Hello and welcome back to the Building HVAC Science Podcast. I also host the Res Talk podcast. You can learn more about the rapidly expanding world of home energy ratings and peripheral topics. And you can find that by going to resnet, resnet.us. That's the Residential Energy Services Network. In this episode, Eric and I speak with Gary Klein, a good friend of mine and a veteran in energy conservation, particularly hot water system design. Gary likes to say he's been in hot water for at least 30 years. Gary tells us about techniques I learned as I was designing my house and the wet rooms or rooms that took hot water, basically. Gary's got a tremendous amount of experience about right-sizing plumbing systems, and he shares some personal anecdotes from his really extensive career, including time in Lesotho, where he implemented solar energy solutions and lived there for, I believe, 7 or 8 years. Right now, he's focusing on air source heat pump water heaters and has a lot of intriguing thoughts there, which include giving Eric Kaiser some things to test in his own home. So without further ado, we'll take you into the conversation Eric and I had with Gary Klein on the science of hot water, insights and innovations with Gary Klein.
Hello, everyone. Welcome back to the Building HVAC Science Podcast. Eric Kaiser here again, Bill Spohn right over there. And we've got another special guest with us today. He's been in hot water for more years than I've been alive. Mr. Gary Klein started in this industry in 1974 with a focus on energy conservation and has been doing all kinds of stuff ever since. So, Gary, welcome to the show.
Thanks for having me here, Eric and Bill. Thank you.
You're welcome. Gary, I think we met back in Colorado. No, maybe at an Affordable Comfort.
Affordable Comfort, for sure. It's been a while.
You put tape on the floor. I remember this. Can you tell us about when you put tape on the floor? And what does that mean?
I've been trying to explain the logic of hot water system design for many, many years. Certainly since about 30 years ago when I got really focused on hot water as a system. And the question is, how do people viscerally understand the distance between things from the point of view of the water in the pipes? And so the tape on the floor idea came about because I wanted to show real distances between the wet rooms and the water heaters in typical construction, and then have us measure how many feet and how much time it takes for the water to get from point A to point B. Bill and Eric, do you know anyone who waits a long time to get hot water somewhere in their house after they turn on a tap?
Yep, kitchen.
Great. So, Bill, how many square feet is your house?
2,900.
1 story or 2?
2.
2 above basement or 2 including basement?
2 above basement.
Water heater's probably in your basement because you have a basement.
Yep.
Okay, we don't get basements in California. We get garages. And so water heaters tend to end up in our garage, not in our basement because we don't have one. If you wait a long time, I'm going to guess it's upstairs in the master bathroom on the 2nd floor. And if it's true, that bathroom is as far from the water heater as physically possible if you take a diagonal between point A and point B.
Well, you're wrong because I listened to you before.
Okay, good.
When I saw you at Building Science Summer Camp, I took copious notes, photographs, contacted you afterwards. And when we designed this house, we put the master bathroom and the powder room and the bathroom upstairs all within about 20 square feet of each other. It's the kitchen is the only one at the long run.
So that's always the second guess. It's either the bathroom or the kitchen. And it's because of that's the way we design and build houses. You listened, thank you, I really appreciate it. And you built a stack, a plumbing stack, within some reasonable distance of the rectangle for the wet rooms is a reasonable percentage of space. Most builders don't do that anymore. They don't think about the relationship of space from the infrastructure point of view, whether it be HVAC systems or water heating systems. They think about it because an interior designer says you need to put this here to make it look pretty. I don't mind making things looking pretty. I think that's essential. Houses have to be good houses. Dwellings have to be good dwellings. They have to function well. But that doesn't mean we can't be better in our infrastructure discussions inside the building, the spaces behind the walls and under the floors. And so the kitchen is the other case because you have one stack and you fit everything you could in one stack and the kitchen's got to go somewhere else. So the kitchen's on 50 feet away across the basement. I don't know, pick a number. And that's not uncommon. So what we do with the tape is we lay out the floor plan of a typical 2-bathroom, 1 laundry room, 1 kitchen dwelling on the floor of the classroom. That's what you saw back then. And we use blue painter's tape to lay out the walls. Then we use tape and the sinks. We lay out all the fixtures, the tubs and the washing machine and the kitchen sink and the dishwasher. They're all laid out on this floor plan because we built the wet rooms. And we put the distance between the water heater and the furthest wet room to be around 50 to 60 feet, because that's really typical in dwellings. I'll come back to how we get that number. And we then use tape of different widths to represent pipe of different diameters. And we lay out the typical plumbing that's built in the United States houses. That's what we do. And then we have you get up there with a tape measure and we walk the tape. And we see how many feet it is from the water heater to the first fixture. And invariably, that first fixture takes more than 30 seconds to get hot water. That seems impossible. You can see one to the other. They're only 10 feet away. You forgot vertical, and you forgot the real flow rates, and you forgot the fact it's 3/4-inch pipe. And so all of a sudden, volume is very, very large. And then we walk around the whole building and we estimate time to tap at every fixture in the house. And then we ask you to fix it. You don't like it? I don't want to wait 2 minutes to get hot water in the bathroom or the kitchen. Great. Fix it. What would you do? So that's been recorded and it's on our company's website at GaryKleinAssociates.com. There's a section in there called writings and another section called videos, I think it is. And under videos, the International Association of Plumbing and Mechanical Officials recorded me some years ago teaching this class. And they recorded a couple of hours of sessions in small increments. And you can see this, and I think it's in section 3 or something like that, 3 or 4. I don't know the exact one.
I found it. We'll be sure to put that into the show notes, your website, and the link to the water.
That'd be great. So that explains what we did. And the reason I did it is so that people could experience the water flowing. You could estimate 1 foot per second, count 1, 1,000, 2, 1,000, 3, 1,000, et cetera, and move your foot, run in front of the next. Just keep walking at that speed. That's 1 foot per second.
Is that about the flow rate in a 3/4-inch?
It depends on the gallons per minute. But the problem is that we forget that water flows at a certain velocity based on the diameter of the pipe. And so a gallon of 3/4-inch pipe is about 40 to 50 feet long.
Well, and we've also gone to lower flow faucets and shower heads in a lot of cases as well to conserve, so people use less water when they open the taps all the way up. So that slows that down too.
That's one of my other favorite pet peeves. So we changed legal flow rates in the United States in the mid-1990s. We should stop calling them low flow fixtures. They're legal fixtures. And in California, we have different legal fixtures than they do in some parts of the country. Because we're California, we have lower numbers for some things, but they're legal flow rates. If you go below legal, now it's low. But the other problem that you've raised, Eric, which is a fascinating thing, you're absolutely correct. Our flow rates are lower now than they were when the pipe sizing rules were developed. So let's see. The rules for sizing domestic water supply pipe in the United States were first published in 1940. By a fellow named Roy Hunter, who at the time was with the National Bureau of Standards. We now call that the National Institute of Standards and Technology, NIST. Gaithersburg, Maryland, there's a plumbing tower that was built in the 60s after Hunter retired. But nonetheless, he wrote down the rules for pipe sizing in 1940. And Eric, as you observed, nothing flushes or flows at the rates it did in 1940, but we haven't changed the rules for pipe sizing. The rules in the plumbing codes and the plumbing engineering textbooks are based on the 1940 publication of Hunter. Now, IAPMO has led a group for some time now, the Water Efficiency Standard Group. And in 2010, we started a project looking at right sizing to bring it into the modern era. And we stand published in 2017. Its 2017 standard included this new method of sizing water pipes based on what's called the water demand calculator. And for indoor fixtures that are typically found in residential occupancies, there's now a new method that allows you to do a better estimate of what the peak demand will be. It's since been published in the 2018 and 2021 and 24 Uniform Plumbing Code as Appendix M as in Mary. 10 states have adopted the water demand calculator as part of their state plumbing codes. It's usable in all jurisdictions in the United States and Canada. If you choose to, you can adopt it because it's a nationally recognized standard. And what it does is it takes, as an example, 35-unit apartment building. This is fun. It's great fun. 35-unit apartment building built pretty much anywhere in the United States would have an estimated peak demand of what do you think? What do you think the plumbing code would say to expect the peak demand for water flow into the whole building? Hot and cold combined.
In gallons per hour?
In gallons per minute.
Gallons per minute. Okay.
And so one way to think about it is to ask yourself how many showers would be on at the same time during the peakiest hour of the peakiest day. Out of 35 apartments, how many do you think will be on at the same time?
Maybe 20.
20 out of 35.
Sure.
Okay, so that would be on the order of 40 gallons a minute. 2 gallons per minute per head is a fair number.
Yeah.
Is that fair?
Sounds good to me.
Bill, what do you think?
Yeah.
Okay. We have measured data for that particular group of buildings because it was phase 1 and phase 2. And the peak demand for hot water never exceeded 3 gallons a minute, which means 2 showers.
Well, this was California, right?
No, this was upstate New York.
That's right.
I was going to say, because California, that's a good point, because they're only allowed to take, 15 or 20-second showers there, so you don't use up all your water.
I've tried very hard to stay out of that particular part of the conversation. I don't want to tell you how long or short a shower to take. I want to get rid of the wastes that are unintended behind the walls and under the floors.
Fair enough.
So, the national average shower is 8 minutes long, by the way.
Did not know that.
But because you wait for hot water to arrive at your showers, on average, your first 2 minutes are waiting in the United States, waiting and adjusting. So I want to give that back to you in your shower. I want to get rid of the waste so you can actually take an 8-minute shower instead of the 6 you're getting now. I want you to have the advantage of the hot water showing up quickly. That's a real big advantage, isn't it?
Or you start running it and you leave the room.
Oh, yeah, when you come back.
And then it may be ready. Who knows when? People lose track of time.
5-10 minutes later.
So when did the hot water get there? I don't know. Beat you.
Yeah.
And so that turns out to be a classic problem as well. And we call that the difference between behavioral waste and structural waste. The structural waste is what we built into the plumbing. Behavioral waste is what consumers do with that information. The best example I've ever heard in my classes was that someone said, I live in a condo and I get up and I turn on the tap and go take a 20-minute nap.
I've been in some buildings like that.
So there's serious problems. I want to get rid of those silly things. So anyway, we've talked about the layout of the plumbing, the right sizing. So that particular project, the plumbing code for that upstate New York apartment building came back with 70 gallons per minute as the estimated peak.
Wow.
The water demand calculator came back with 14 or 15 gallons per minute at the estimated peak. The pipe size is the big deal. The building came in with a 3-inch main, according to the code. With the water demand calculator, it came back at a 1.25-inch main.
Wow.
That's a significant difference.
That's a big, big difference. And so you still have to size the piping so that you have enough residual pressure at every fixture to have things work right. You want to make sure your shower heads work right and your toilets flush properly and everything is working correctly. You need minimum available pressures for that to happen. But as long as you've properly accounted for that, you don't need a 3-inch main to do it. You can come in with a 1.25, 1.5-inch main. We actually looked at a design for a 92-unit apartment building in Seattle that came back needing a 1-inch main for 92 apartments, which I have to tell you, nobody would think is possible.
They wouldn't believe you.
No. They don't believe the hydraulics. So
most houses have a 3/4-inch main coming into them for a single family house.
So it turns out the more dwelling units you have, the greater the possible diversity.
Yeah.
Everyone's got very different schedules. And so even though everyone in your whole building might be off to work to be there by 9 o'clock, they all have different travel times. So some get up earlier and some get up later in order to get there by 9 a.m. or 8 a.m. And that variation means that the peakiness doesn't matter.
Some may get up and take a shower first before they have breakfast, and some may have breakfast and then take a shower or work out somewhere in there or walk the pet or who knows.
All of those things are possible. So if you've got 90 people, 90 apartments, you have 90 possible diversities. Start times, it could be that different. And because there's very little hot water use is actually fairly short in terms of things during the day. Showers, because it's so short, there's very little potential for overlap, I guess is the point. You flush a toilet. Yes, it has to refill with your 1.2 to 1.6 gallons. But when it's done, it's done. It's over. It's not continually running. Showers have defined times. Anyhow, so the right sizing project is a really big deal. It's called the water demand calculator. There's a website. iAtmos supports a website for it because they're the sponsors of it. And it all works.
You have another interesting aspect to your background, and it's an audio podcast. People can't see it. There's a piece of art over your shoulder.
Yes, 3 women.
Yes, and it's reminiscent of, looks like a African cultural.
Yes, that's right. I married in Africa in 1979.
No kidding.
Really, truly. So let's back up. You need to ask me, Gary, how did you end up in Lesotho? So go ahead and ask me that question.
Hey, Gary, how'd you end up in Lesotho?
Phone call. I answered a phone call. So what do I mean? So in 1974, I wrote the proposal for my undergraduate degree at Cornell to study technology and society with an emphasis on energy conservation and renewable energy. When I graduated in 1975, I couldn't figure out who'd hire me, so I started a consulting firm with my buddy Alan. And we're working along in Ithaca, New York, and Alan gets a call one day from our colleague Jack, who'd gone back to the Canadian government to do energy policy. And he says to Alan, can you go to Lesotho to do wind energy research? Alan said, sure, where's Lesotho? You have to understand that the last time we took geography, it had a different name. And we couldn't look it up on Google Maps, and we didn't have an atlas in our office. We narrowed it down to one of 2 countries without a map. There were only 107 countries then, and we were both pretty good with that stuff. So we figured out where it was. And so a year and a half later, Alan goes to Lesotho for 3 months. It was a short-term project to do some wind energy research for them to see about the possibilities of installing wind generators. All good. We close our business. I move to Syracuse. I take a full-time job with somebody you probably know, Larry Kinney. I'll buy a house and settle into a career path. I'm there a month. Alan calls from Lesotho and says, they don't need me, they need you. Can you come? And I said, sure. And he said, what about your job? I said, well, if they don't give me a leave of absence, I think I'll quit. Now, you have to understand, my degree had been intentionally designed to be able for me to be plunked down anywhere in the world and improve the energy situation as it was where I was dropped, using local materials and skills. That's what I had designed my degree to do. Someone was giving me the chance to do it. Why wouldn't I take it?
Unbelievable.
Actually, 9 months later, I ended up in Lesotho. It was pretty quick compared to Alan's journey. And I went there for 6 months. I stayed 7 years. And I met my wife on Christmas Day in 1979 in the mountains of Lesotho. And we've been dating or married since the day we met. It'll be 44 years this year. Is that right? Yeah, it'll be 44 years this year of marriage, 45 dating.
Sure.
Anyhow, that picture that you see behind me is of 3 women carrying water and babies walking into the sunset. So that's a tapestry from Lesotho.
What does it mean you created the energy policy, like a handbook or a set of documents or protocols? What does that actually mean?
So where, in Lesotho?
Yeah, in Lesotho.
I was hired to do energy research and development. I was hired to do energy policy for the state of California.
Oh, okay.
So apologize for any confusion. But we had some really unique things happen when we were in Lesotho. We were given access to all of the recorded temperature data that they'd gathered around the whole country since they'd started gathering it. And it was all on paper. And we had to look through reams and reams of paper from 20 or 30 recording sites around the country, where basically the churches, the priests, and the convents, the nuns would write down the temperature data every day all throughout the country, because that's where they were willing to put recording stations. And they were spread pretty far around, and you got all sorts of good stuff. We were able to look at the solar gain from 2 different sites. That was the actual sun gain by recorded instrumentation. And we got a chance to look at the weather data for the whole country and figure out the climate zone of Lesotho. There's actually 3 climate zones because of their elevation change. And there's really only one solar regime because the country is so high above sea level, it has very little interaction with clouds and general weather. Lesotho, I went there from upstate New York, which has arguably 330 cloudy days a year. And I was doing solar work there, and it was successful. And I went to Lesotho with 330 clear days a year. Paint it dark, put it in the sun, it's going to work. I mean, it can't be that hard. So I installed my first solar thermal panels in 1974 and my first PV panels in 1979, like the Pliocene era of PV.
Right.
Would you like to have lights? Would you like lights? Would you like lights? Because if you want anything else, it's really hard. You can have lights. It was a long time ago.
Were you building a house there then, or was this on an existing house that you put solar onto at that time?
I put solar thermal in the United States, not on my own home, but I taught people how to do it in the early 1970s, mid 1970s. And then when I went to Lesotho, I got the opportunity to help the clinics around the country put in PV panels to run their two-way radios. There's the flying doctor service was big in Lesotho at the time, and they would fly doctors and nurses out to clinics all over the country. As long as you had an airstrip, they'd show up every once in a while on a schedule. Well, in order to have that be on that schedule, you had to have a two-way radio. And the question is, how do you power your two-way radio? Because it takes electricity, and we're in the middle of nowhere and there's no grid. So that means generators or recharged batteries. And it turns out that PV is a really good choice for that. So we installed our first PV panel in 1979 for a clinic in the mountains of Lesotho. And then other doctors heard about it and they wanted PV power for their clinics. And so every time I'd see a new doctor from the remote areas, they'd ask, can we have dinner and talk to me about what to do? And I ended up starting a business selling PV panels in Lesotho in 1984. In the meantime, we built our house in Lesotho, passive solar heated and cooled, gray water separated from black water. What else did we have? Solar thermal for hot water, PV for running electricity for the house. We had gray water catchment and rainwater catchment. Does that sound like a lot of the stuff we're trying to get people to do now?
Yeah.
Yeah, a little bit.
Okay. We didn't know we couldn't do it. We just tried. We had really good local building materials. I'm pretty sure that all of the materials in the whole house came from no further than 300 miles away. But the closest building materials came from our foundation. And the lot we had was my father-in-law's plot of land. And we built a house there. And there was about a foot of topsoil, and underneath that was clay. How good a clay do you ask? Well, good enough they wouldn't pass a perk test.
That's good clay.
And so we dug out the clay down 3 feet so we could put in a deeper foundation. I wanted that. And so all the clay came out of that foundation all around the whole house. And we had to dig drainage trenches for the leach fields for the wastewater treatment system. And so we dug out all of those trenches and we wheelbarrowed the clay to my neighbor who had a kiln. And he fired it into bricks and he wheelbarrowed back the bricks. And that's how we built the house. I'd say that's local building materials 101. That's like
throw up a kiln and go to town for building your house. You don't have to truck it very far.
Well, he already had the kiln. I was just using a local resource that happened to be nearby. He was literally 100 yards away.
So what keeps you busy lately?
Most of my work in the last several months has been on heat pump water heating, air source heat pump water heating. I continue to stay very involved in the right sizing effort in the United States for plumbing. I'm leading a few different national committees and working groups on those topics, both of them, because it's so important to get the right sizing to be part of our normal course of business. The air source heat pump water heaters have been a focus lately because if we're telling people that we're putting in this new type of water heater that uses air to make hot water, electricity aided air to make hot water, I want it to work as a heat pump to make hot water. Don't you? Most of what's sold on the market today are hybrid heat pump water heaters, which means they have electric resistance elements built into the tanks. And the reason that they're there is because the people in the room, when the DOE changed the rules for efficiency of water heaters, were the big three water heater manufacturers. Rheem and A.O. Smith and Bradford White were all in the room because that's the ones who make water heaters for the United States. They make about 9 million or so a year. And someone's changing their business, they want to be in the room. Well, there were no split system heat pump water heater manufacturers making water heaters back then, and they weren't in the room. And so when you go back to your factory afterwards and you say, what are we going to do to meet this DOE requirement? You look around and say, well, we have electric resistance water heaters. What if we added a refrigerator compressor on top, made it run backwards, and we'd end up with hot water? I'm not trying to minimize the level of effort it takes to make a product like that work, but I'm pretty sure that's what happened. because they're really good at making tanks, and they're really good at shipping tanks, and they're really good at packaging, and they have an entire infrastructure to make water heaters that are like that.
But not splits.
$9 million a year. And so you go back to the drawing board and say, what do I have around me that I can do? That's what they have.
My water heater is an air source heat pump water heater. And I swear the efficiency mode runs the electrical element. I have to override that to heat pump only. But I think the efficiency mode means it's efficient for customer service, not to have to deal with complaints.
I think that's right. So you have a basement, right?
Yeah.
What kind of heating and air system do you have, Bill?
Air source heat pump for the whole house.
Great. Central fan or splits?
Distribution fan, yep.
Great. You should follow what our friend Gary Nelson's done because he's solved the problem. I don't know if you've done it. So Gary's been renovating his house in Minneapolis for some time, as you know, and he has a mechanical room in his basement. And in the mechanical room live three things: the indoor air handler for the HVAC system, the air-to-air heat exchanger, because he doesn't want to lose all the energy in the air when he brings in fresh air, and his air source heat pump water heater.
Same thing I got.
He only has one duct system. He only has the HVAC duct system, except for the supply air for the
fresh air,
bringing in the new air, fresh air, and the exhaust air. That path has to be in and out. But the new air comes into the mechanical room and dumps on the floor. The HVAC fan runs 24/7 on really low watt mode, okay? Because you can do that now. We've got equipment that does this. And the cold air that comes out of his heat pump water heater dumps on the floor of the same room, and the HVAC fan air handler pulls it in and distributes it throughout the house. So the temperature, the cold air coming out of the heat pump water heater is distributed and diluted with the air return of the whole house. And so his heat pump, he has to override it too, is running in heat pump only mode. And he's making hot water and the cold air isn't felt anywhere. His furnace, his HVAC return comes down the stairs through the open door to the basement, and it goes through the mechanical room doorway with no door and gets sucked into the fan. He's allowed for lots of airflow with very little resistance and has lots of dilution air to make it work right and not feel bad to consumers, because you've got to distribute that cold air. You have to get it away from the heat pump. Otherwise, you'll contaminate the source air with cold air, and that's not what you want. You want warm air.
That's an interesting thing, because I've actually talked to a couple of water heater manufacturers about doing that very thing and tying it in with HVAC systems, because I thought the same thing would work really well. I also have a heat pump water heater in my basement and had planned to duct that into my return so that I mix it with the house better.
The HVAC fan is extremely powerful in comparison to the fan that comes with the heat pump water heater. And so using that fan to suck air is a good idea, because too much air is not a problem. Too little air is.
So if you try this on for size, I'm curious what you think about this. I plan to duct that water heater into the return with essentially two closely spaced T's, some of how you do a primary secondary loop system in a hydronic heating system, and just use that continuous air flowing past it from the HVAC fan, turn on the fan in the water heater, pull a little bit of air out and dump it right back into that return. Actually, my plan had been to do it after the air filter from the rest of the house so that I'm pulling clean air through that water heater and I don't have to worry about getting dirty.
I like the idea of pulling the already filtered air. The filters on the heat pump water heaters are small.
Terrible. They're kind of like a ductless split unit on the wall.
Yes, the filters are going to have challenges, and there's no obvious way to clean the coils because they're sitting in the middle of electronics in the middle of your basement. It's not going to be easy to maintain them. So the cleaner we can keep the air, the better off we're going to be. What I think you want to be sure to do is to turn the furnace fan on every time the heat pump runs. Have a relay that tells that fan to run. And then I almost don't care. You could do a good job of putting in you have one air entrance to your heat pump water heater, top or side or something like that?
Correct. The manufacturer has a boot that fits right on it for an alternate intake.
Yeah, you've got the tools. Measure the pressure losses and measure the airflow.
Yeah.
Because I worry about decreasing the airflow by inadvertently putting in too much pressure that the fan is not designed to overcome.
Oh, on the fan on the water heater.
If you have an axial fan, which is the type that we got first, their ability to overcome back pressure and ductwork is approaching zero. It's not good. And so you really want to make sure you've oversized your duct system, not downsized it. You're just trying to direct the air in the right direction. If you've got the centrifugal fans, which some of the companies have started to come out with, you've got more ability to overcome back pressure and ductwork. And so you have less of an issue, but you don't want to restrict it in any fashion. The COP of the heat pump is based on the ability to get a delta T through the coil times the airflow rate. And if you lower the airflow rate and you don't have very high delta Ts, you're not going to get much heat out of them. And the point was to get the heat out of them. So when we see each other, you're going to bring me a sketch and we'll look at it, maybe take some pictures of your basement so I can see what everything looks like that's in your head before we meet. And then we'll have a cup of coffee or whatever and we'll discuss it.
You don't even want to think about what's in my basement right now. It's a mess.
I'll show you mine if you show me yours, dude. Mine don't look any better, and I don't have a basement. We have garages. They're just terrible.
That's trying to put 10 pounds of stuff in a 5-pound closet at the back of the garage. I've seen those California garages before.
Is there any place where there's the collected wisdom of Gary Klein exists? You touch on so many different topics, and it's like, where do you begin? Like I said, I benefited from seeing your compact water stack, wet room, cold water, hot water thing. I was in the process of laying out our house design, and I put that to a stop until after we adopted most of what you said. But how does somebody learn about this?
That's one of the reasons I do podcasts, is so that they can get recorded. The other is, it sounds like you're telling me I ought to write a book or something like that, and that's been suggested for many years. I'm just busy, and I don't choose to direct my time to the writing.
Right. Your website is a good starter, but there's a lot of depth and richness, and illustration, I think, is really important when it comes to this. Just like where we started the conversation was making people become water and take the flow path.
Yeah. By the way, I thought about building the house to scale because I was worried I wouldn't have enough space in a room. So you're sitting in an office at your house. Eric, I can't tell where you are exactly. It looks like you have a background of some form, but it could be your office.
That's the office. That's all real back there.
Cool. Bill, how many square feet is the room you're in, roughly speaking?
Say 11 by 12.
Good. So you've got 11 foot in one direction, 12 in another. Close enough. Doesn't matter for this. Imagine there's a water heater in one corner, and the diagonally opposite corner is a fixture. A sink or a shower doesn't really matter. How many feet of pipe will be there between the water heater in one corner and the fixture in the other corner? I'm going to give you a clue. It doesn't run diagonally, so you have to do the limbo under the plumbing.
Oh, no.
It follows rectilineal spaces.
Shoot.
Isn't that how we build? Plumbing follows the spaces that are between the walls and under the floor. So it's got to go either up or down from the water heater to get to the floor or the ceiling. We'll go up to the ceiling. I have to go 11 feet in one direction, 12 in another. That's 22 feet plus a 5 up. And I got to come back down at least 5. I'm at 32 feet, 33 feet. I haven't gone across your room yet.
We don't appreciate what's behind the walls and under the floors.
Right. And so that distance turns out to be really easy to build in a classroom. I only need 50 feet to get across a typical house, and most are bigger. I don't have to prove it gets worse as houses get bigger. I have to prove it's bad in small dwellings. It's not good in small dwellings because distance, horizontal distance, is hard to overcome. You have no choice. By the way, the best, most architecturally compact dwelling we've seen so far has the hot water system rectangle, the water heater and all the fixtures. Takes up less than 1% of the dwelling's floor area. One-story house.
Wow.
Back-to-back bathrooms on either end of the back-to-back bathrooms is a laundry room and a kitchen sink and dishwasher. And so it's got one plumbing wall that's on the order of 10 feet long. And because of the design, they hung the water heater, tankless gas at the time, over one of the two toilets. And then they put a mini manifold cabinet behind over the other toilet. And all the plumbing runs sideways. There's virtually no vertical height to change.
That's the other aspect that I tried to do here and failed at convincing the plumber to do it. Home runs back to the water tank, hot water tank.
So that may or may not have been a bad thing. This particular one was done with home runs because of his construction. This is a Habitat for Humanity house, and he has all volunteer labor. It's really easy to teach someone without very much plumbing skill to say, cut this pipe, run it from here to there. Do that 6 more times and you're done for the day. The plumber comes by and connects all the pipe up properly. But trunks and branches are harder to teach volunteers to do because you don't understand what connections are going to go where. And so you have to build it as you go. So you need more skilled labor for more of the job. What we tend to teach is trunks and I call them trunks and twigs. I don't like branches. By my definitions, a twig serves a single fixture, hot or cold water. A branch serves 2 or more twigs of the same temperature, hot or cold. And a trunk serves branches and twigs. That's the logic I use to teach this stuff. And so your sink has 2 twigs, a hot twig and a cold twig. And you want that connection to get to the source of hot water, the trunk, as quickly as possible. And so I try to lay out the plumbing so that I have no branches, ideally, unless the pipe serving 2 fixtures is the same diameter as the twigs would be. And I try to keep the length of the twigs on the order of twice our height, roughly 2 cups or less. So let's work backwards on that. And then I think we're going to have to wrap this up. I think we're at our time limit here. How to describe this. So I'm about 5'10". How tall are you, Bill?
5'8".
And Eric?
6'4".
Cool. We're all about the height of 1 cup of water in half-inch plumbing. Okay?
All right.
If you know someone who's 5'2" to 5'4", that's half-inch copper type L. If you know someone who's 6'6", 6'7", and 6'9", up to 6'9", it's plastic plumbing. Half-inch plastic. Either CPVC or PEX, doesn't really matter. They're about the same inside diameters. And so we're all about the height of about 1 cup of water. If you want hot water to show up in no more than a cup, you can't have more than a half a cup in the pipe that's not already hot. Well, a half a cup is like 3 feet. The closest fixture to the floor in your bathroom is the sink fixture. That's the angle stop. And we'll stipulate that you've got to go 18 inches down to get into the floor, a foot down to get in the floor. You got to be in the middle of the floor. You could get to the sinks within 3 feet of plumbing. Showers are 4 feet off the floor. You can't get there in 3 feet. You need 5 or 6 feet to get there in practical plumbing terms. And so what I teach is that the length of the twig shall be no longer than twice the height of the shortest person on the job. It's a good goal. And if you have a really tall floor plan, really tall floor to ceiling heights, I'll give you the floor to ceiling height to get down to the sinks if you have to plumb from above down. That's the magic.
So I got one more question for you. You started this out by talking about hot water getting around to everything really fast. And when I plumbed my house, I did it with a system called gravity recirculation. Thoughts on that? Is it more energy efficient? Because you've probably done all the calculations, I'm going to assume, at some point in time. Is it more energy efficient to do that than, say, an electrical circulation with a pump?
So compared to the pump, yes, it's more energy efficient because you don't have the pump operating cost. But thermally, you have the same losses, oddly enough.
Okay.
So a gravity circulation loop has a relatively low flow rate, which means it needs a relatively high delta T to operate. And so if you're able to measure that, you still have your gravity circ system?
It's a double T, so it comes up out of the water heater, goes 2 directions so that I can get water to both ends of my house since the water heater's in the middle.
So you have a 2-zone plumbing system. I like it.
It has one uninsulated riser on the return, and that's my delta T there. Everything else is insulated in it.
Great. I want you to take temperature readings.
Okay.
And I'm going to guess, is it copper or plastic?
Mostly copper, except for the vertical riser, which is plastic, because I didn't want the vibration from the water heater, from the heat pump water heater.
Great. You're going to take a couple pictures, and I'd like you to get temperatures before you leave this week.
Absolutely.
Copper's a bit problematic to get temperatures on. Bill knows how to do this, so you guys figure out how to take temperature readings on copper pipe. You can't use your thermal camera unless it's specially tuned.
I'm an HVAC guy. I can take copper temperatures all day long.
Good. I need to know what they are. You can set it up. Given it's a gravity loop, you can put a piece of tape on the copper pipe. It'd be fine. Or you can spray paint it any color you'd like. Turns out black doesn't matter. It's just the surface that has to be fixed. But anyway, take the temperatures and we'll do the math when we see each other. But fundamentally, the heat loss of the loop is almost exactly the same with gravity as it is with a pump.
Interesting.
The pump moves the water faster and has a lower delta T. You have a higher delta T and a lower flow rate typically. And so what I prefer to see, you don't pay for the cost of running 1 or 2 pumps, which this system would need. But what you're not getting, you're running it 24 hours a day. So whenever you wake up, hot water's wherever the pipe is, it's hot in the pipe throughout the house. And so now you only have to clear the twigs and branches. And so that's how yours work.
I'm just paying for that heat in the pipes.
You're paying for the heat in the pipes. And with heat pump water heaters, I really don't want to take that much heat out of the water heater all day long. It's a problem. They're not designed to have heat taken out in continuous streams. They get mad at you.
How so?
You tend to bring back too warm, cold water. And they don't like hot, cold water. They like cold, cold water. That's why we want to measure the temperature.
Because I've been running it on heat pump only mode since I put it in there. Haven't had any problems.
Good. That's why I want to get measurements. I don't trust any of this stuff until I see numbers. It's good.
Love to share them.
With that, we're going to wrap it up.
Bill says, now we're talking numbers.
Any closing thoughts for our listeners, Gary?
Yeah, I think that the key is to pay attention to real use and real patterns. Don't guess. And we should be modernizing our methods of sizing. We have to pay attention to make sure that heat pumps, water heaters run in heat pump mode. Ideally, we're not going to scavenge from the house temperatures to make them work right. We're going to end up with heat pumps that run from outdoor air temperatures throughout the country. They're coming. If we don't have them yet, they're on the way. It's the logic of all that makes sense. And we just have to do a much better job of integrating all the technologies together so that they work well together. Everybody who sells his products tells us they have the best thing since sliced bread. That may or may not be true, but if we don't make good sandwiches, the customer will be unhappy. We have to make sure that the stuff we put together works well together, not just on its own.
I think he even said something like that, water as a system.
I did at some point in the past, yes.
Very good. Thank you. As always, an enjoyable conversation, and we're really looking forward to seeing you in person. This episode will come out after we meet at the Building Science Summer Camp, but you'll see Eric and I there just in a few short days.
Cool. Looking forward to it.
Thank you, Gary.
Thanks, Gary.
Thank you.
We appreciate you taking time to listen to this episode of the Building HVAC Science Podcast, where we chatted with Gary Klein on insights and innovations in the science of hot water. In the show notes, you'll find a link to Gary's website. As Gary mentioned in the interview, he's got a lot of links and recordings to some of his presentations. Maybe you can email him through that and ask him to finally write that book, because he really does need to write a book on this, or at least some kind of document that can be shared. Tremendous learnings, tremendous education on the science of hot water. We also give a link to the IAPMO water demand calculator that he mentioned, which improves the sizing and calculations of water demand. And we also give a couple links to Larry Weingarten's books, The Water Heater Workbook, A Hands-On Guide to Water Heaters, and The Philosopher's Wrench, using your creativity, heart, and tools to fix the world. Hope you enjoyed this episode, and you come back again to listen to the Building HVAC Science Podcast, which is a production of TruTech Tools Limited. In full disclosure, I'm a co-owner of TruTech. Eric Kaiser is an employee of TruTech, and the opinions voiced are those of my guests, my co-hosts, or myself, depending on who's speaking, of course. And if you're in the market for tools or test instruments mentioned in our podcast, take a look at what we offer at TruTechTools.com, TruTechTools.com. And if you're interested in buying something, you can use the offer code HVACBS for a nice discount. Thanks again for listening to this episode, and we hope you come back again for the Building HVAC Science Podcast. Take care.